At thousands of revolutions per minute, a pristine cutting insert shears away solid steel with predictable, exact resistance. This line graph plots the standard industry definition of tool life. It maps wear size against cutting time, treating tool degradation as a simple economic countdown timer. In reality, tool wear is a highly dynamic, independent variable. Second by second, progressive physical degradation actively alters the mechanical and thermal state of the entire machining process. Ignoring the physical reality of a degrading tool guarantees hidden structural defects and out-of-tolerance components on the factory floor. To understand how a dulling edge ruins a final part, we have to look past the machine envelope and zoom in on the microscopic point of contact between the tool and the workpiece. During the initial break-in phase, a pristine cutting edge reaches a steady state, separating material smoothly and efficiently. But this microscopic junction is immediately subjected to extreme variables: immense shear forces, severe extrusive friction, and a rapid, intense spike in localized heat. This thermodynamic battleground is where macroscopic part quality, both the final surface topology and the dimensional accuracy, is ultimately decided. This schematic shows a 2D cross-section of a pristine cutting tool engaged with a workpiece. Two primary morphological modes tear this geometry apart. The first is flank wear. As the tool drags against the freshly cut surface, progressive abrasion degrades the clearance face. The second is crater wear. High-pressure sliding of the metal chip literally carves a concave depression into the top rake face. Together, flank and crater wear alter the tool's effective cutting radius, the measure of sharpness at the precise tip where the cutting edges intersect. The immediate mechanical consequence of this blunted tip is that cutting forces rise exponentially. The tool is no longer cleanly shearing the metal, it is actively pushing and tearing it. These rising, unstable forces exert massive physical pressure onto the machine setup, causing the rigid tool shaft itself to bend and deflect under the load. This mechanical flexure directly deteriorates the surface roughness of the part. In studies machining difficult alloys like Inconel 718, tool flexure translates directly into heavy surface variability and gouging. A geometric shift of mere micrometers on the cutting edge destroys the mechanical stability of the entire operation, resulting in dimensional variability and rejected parts. While an erratic surface finish is easy to spot visually, the most dangerous consequence of tool wear occurs entirely beneath the surface of the metal. This cross-section illustrates how a blunted tool widens the contact zone with the workpiece, massively increasing extrusive friction at the tool-chip interface. That friction drives a severe temperature spike in the cutting zone, forcing immense plastic deformation onto the surrounding material. Because this intense heat cannot fully evacuate through the ejected metal chip, it bakes directly into the newly machined surface, structurally altering the metallurgy. This creates a permanent, microstructurally damaged hardened surface layer sitting just below the cut. In high-speed milling of titanium alloys, researchers found that tool wear dictates the depth of this damage, creating a hardened layer measuring exactly 20 to 28 micrometers thick. This intense thermomechanical load permanently distorts the molecular lattice of the metal, creating a residual stress profile. Under worn tool conditions, the metal develops extreme compressive residual stress, the internal force pushing a material's atomic structure together that remains long after cutting. In these titanium studies, that stress peaked at exactly 190 megapascals. Tool wear leaves an invisible thermodynamic signature within the part. This degrades fatigue life, massively increasing the risk of catastrophic long-term failure in the field. The workpiece material itself acts as the primary accelerator of this wear curve, dictating exactly how fast the geometric and thermal degradation occurs. This comparative matrix plots two distinct wear rate curves. On the left, plain carbon steel follows a slow, linear upward slope, but modern aerospace alloys generate a violently steep exponential wear curve. Materials like Ti6Al4V or nickel-based superalloys share two intrinsic culprits: extreme high hardness and very low thermal conductivity. Thermal conductivity is the physical property that dictates how efficiently a material transfers heat through its structure. Because these alloys are poor thermal conductors, they create a thermal trap. The massive heat generated by friction cannot safely evacuate into the metal chips. Instead, this trapped thermal energy is forced to accumulate directly at the most vulnerable point, the cutting edge of the tool. This localized thermal buildup softens the tool matrix, immediately accelerating both adhesive and abrasive wear mechanisms. This creates a destructive feedback loop. Higher initial wear increases friction. More friction generates higher heat. That heat further softens the tool, causing even faster geometric degradation. The end-stage results of this runaway loop are severe subsurface damage, localized microcracking, and wildly uneven micro-hardness profiles across the machine's surface. Without engineered interventions, the intrinsic thermal properties of tough aerospace alloys guarantee runaway tool failure and compromised part integrity. Preserving part integrity requires active interventions to break this thermal-mechanical degradation loop. Advanced structured tool coatings act as the first line of defense. These thin film layers physically shield the substrate material, delaying the onset of abrasive wear. Next, programming adaptive tool paths and optimizing feed rates mechanically stabilizes the cutting forces, preventing the initial tool shaft deflection that ruins surface finish. This split screen illustrates the primary thermal solution for tough alloys, minimum quantity lubrication, or MQL. MQL is a precise cooling technique that delivers a microfine aerosol of cutting fluid directly to the cutting zone, often enhanced with nanoparticles. By targeting heat accumulation exactly at the tool chip airface, MQL drastically lowers cutting temperatures and reduces the chemical reactivity of the workpiece. These systems are active defense mechanisms engineered to preserve the geometric and microstructural integrity of the final component, rather than simple cost-saving measures. Precision machining requires the careful management of a highly volatile thermodynamic system, well beyond the basic mechanics of cutting metal. Microscopic tool geometry dictates friction. Friction generates intense heat, and that heat dictates subsurface survival. True quality control in manufacturing demands mastering the tool wear rate through carefully engineered materials, optimized parameters, and advanced fluid lubrication. In the modern industrial landscape, understanding and controlling the microscopic physics of tool wear is the only way to guarantee macroscopic performance and long-term safety.